Welcome everyone to our seminar this week, where our speaker is Frederik, who will speak about generalized derivative spinors on Courant algebroids.
Please. Thank you. My voice may not be working ideally, so I'm a little bit sick, but that is not going to stop me. And so, as you can see, the topic I'm going to tell you about is, well, it's a work in progress. It's about a project we are working on together with Frederik Ďalak. And so, as you can see, our aim is to construct a Lie derivative of spinor fields on Courant algebroids. So the problem of defining the Lie derivative for spinor fields has been previously addressed and studied in classical geometry on smooth manifolds, for example, in the work of Bourguignon and Godot. And so the first thing I'm going to do is to kind of give you the introduction to the classical version of this problem. And then I'm going to tell you about what kind of modifications and changes need to be made in order for this formalism to also apply in the setting of generalized geometry on Courant algebroids. So I'm going to begin with the introduction to the classical case of the problem. So here I'm going to tell you first about the Lie derivative itself, and I'm going to give you the idea of why it actually kind of becomes a problem to define it for the case of spinor fields. Then we are going to look at how an equivalence of two different metrics on a given vector space may be established. And then we are going to basically use this knowledge to define the Lie derivative of spinor fields. Here I should mention that properly I should be talking about spinor fields rather than spinor fields this whole time, because we are focusing on the grid group rather than spin group throughout our work on this. But as well, the two cases are analogical enough so that basically everything I'm going to say is also going to apply to spinor fields. And also I'm kind of used to the word spinor rather than finor. So I may be making this mistake a lot, but more properly we are focusing on the case of finor fields. So let me begin with the intro into the classical version of this problem. So if you think about Lie derivative on your manifold for just a tensor field T in direction of a vector field X, then what one does is to consider the vector field flow generated by X, which is a family of diffeomorphisms phi T of your underlying manifold. And so now if you want to know the Lie derivative of your tensor field T at the point M of the manifold, the first thing you would do is to consider the value of the tensor field T at phi epsilon of M at the infinitesimally shifted point in direction of your vector field flow. Then you compute the pullback again by the vector field flow. This gives you a value, again, a tensor at the original point M, and then you compare it, right? You compute the difference between this value and the original value of the tensor at the point M. And so this difference to the first order in epsilon gives you, by definition, your Lie derivative of the tensor field, right? So this is a very well-known formula. And so we can realize that in order for us to be able to formulate this definition, we need to be able to compute the pullback generated by the vector field flow, right? So in other words, what we need to be able to do is for your vector field flows, being the diffeomorphisms of the underlying manifold, you need these to also induce the corresponding map between tensor fields at the different points of the manifold, right? So, and in this case, naturally the pullback via the vector field flow plays this role. But now, if you think about the spinor fields on the manifold, this actually becomes a problem because there is no obvious analogy for this pullback map for the case of spinor fields at different points, right? Because, well, if you think about the structure of spinors, right? So spinors are defined for a certain metric on a certain vector space. And so if you think about the spinor fields at different points, these are defined first of all for different vector spaces, being the different tangent spaces at different points, and also for independently different metric structures, right? Being the values of your metric at the two different points. And so, right, the vector field flows generated by an arbitrary vector field, they have no way of knowing about this metric structure, right? So there is no obvious analogy of the pullback in case of tensor fields. There's no analogical way to actually induce by the diffeomorphisms of the underlying manifold to induce the corresponding map of the spinor fields at different points. And so this is kind of the core problem that one has to solve and address when trying to actually define the Lie derivative for spinor fields. And yes, as I mentioned, following the work of Bourguignon and Godershaw, we are going to first kind of learn how to solve this problem in this classical setting, and then we are going to look into what kind of modifications can be made to actually bring this over to Courant algebroids. And yes, I believe there is a lot of cool geometrical stuff going on in the background, so I hope you will find it interesting. And so the first thing we are going to do is to kind of change our perspective on the Lie derivative itself. So we are going to, even in the case of ordinary tensor fields, so we are going to view a tensor field instead of being the section of the associated vector bundle. We are going to instead see it as the corresponding equivalent function on the total space of the frame bundle with values in the corresponding space of components, right, with the tensor representation. So this is just an equivalent way to view tensor fields themselves. And now, if you want to compute the Lie derivative of the tensor field in this language, what you can actually construct a lift of the vector field from the underlying manifold to obtain a vector field actually as a vector field on the total space of the frame bundle, which I call XF, right, the lifted vector field. And so this may be done in a very straightforward way, right? If you want to see or have the value of your lifted vector field at the point F on the frame bundle. So this would be some kind of, right, the frame of the tangent space on your manifold. Then what you do is you construct a curve starting at this point F on the total space of the frame bundle. So this may be done simply by considering the vector field flow and pushing forward the frame, right? You just push forward each of the frame elements. And this gives you, right, a family of frames over the points, right? Basically a curve on the total space of the frame bundle, which covers actually in the integral curve of the vector field. And right then you just differentiate this curve, and that gives you the value of your vector field at the point F. And so in this language now, if you want to compute the Lie derivative of t, then what you do is you simply write t is your equivalent function on the total space of the frame bundle, and you simply apply this lifted vector field to this function. As a result, you obtain once again an equivalent function, so it's again corresponds to a tensor field, and that is the result of your Lie derivative, right? And so this kind of point of view on the Lie derivative is what we are going to adopt throughout this talk. So also when it comes to the spinor and spinor fields, we are going to see them instead as seeing them as the sections of the associated vector bundles. We are going to see them as the corresponding equivalent functions on the total spaces of principal bundles, and we are going to construct a lift of a vector field from the underlying manifold to the total space of this principal bundle, and the action of this vector field is going to define the Lie derivative for us. So let's do strategy here. And now this is kind of seemingly unrelated for now, but it's just going to be kind of a piece of the puzzle which we will need to use later on to define the Lie derivative. And so we are going to learn now how to establish equivalence of two metric structures for a given vector space. So let us consider vector space V, and let's denote BV, the space of all the bases of the vector space V, and let's denote by MV the space of metrics on this vector space of signature PQ, being some fixed signature. And it is now easy to actually define a projection map, which is going to make this space BP of bases a total space of a principal bundle for the orthonormal group OPQ over this space of bases, where the projection can be very simply defined as right to take a basis of the vector space and you assign to it the unique metric, which is such that it makes this base is an orthonormal basis with respect to that particular metric, right? And so you can uniquely find a metric like this for each basis, and right, also for each combination PQ, choice of signature, right? And this gives you naturally a situation where the fiber over each of the metrics, the fiber over a particular metric G, right, is going to be given by all the frames which are orthonormal frames with respect to G, and therefore naturally fibers are diffeomorphic to the orthonormal group itself, right? So you obtain a principal bundle for the orthonormal group OPQ. And now what you can do, you can actually establish a connection on this principal bundle by defining the infinitesimal parallel transport between two infinitesimally close fibers. And so this is what it looks like. So if you have fibers over two infinitesimally close metrics, G and G plus epsilon H, being some kind of infinitesimally shifted metric, then right, to define the parallel transport, we need to connect the two fibers, right? So we need to map a frame which is an orthonormal frame with respect to G onto an orthonormal frame with respect to the shifted, the transport metric. And so this is the way you can do it. This is actually a canonical infinitesimal isometry between the two metrics, right? So it's fully given by determined by G and the transformation H. And so it can be easily shown that this gives you to the first order in epsilon an isometry. So yeah, I should mention that this only really works in the infinitesimal case because this connection actually has non-vanishing curvature, right? So if you would be interested in connecting two non-infinitesimally close metrics in a way like this, you would naturally have to choose a path in the space of metrics to connect them, right? And due to the non-vanishing curvature, you would obtain a different result for this parallel transport depending on what path you choose. But here, for the purpose of defining the derivative, as we will see in a few moments, it's actually going to be enough to have this defined canonically in the infinitesimal case. So that's going to be enough for our purpose. And yeah, actually, in the case of positive definite signature, you can actually connect each two metrics canonically by canonical path, right? So in that case, it can be figured out. But we are focusing on the mixed signature. So in this case, it works canonically only in the infinitesimal case. So yes, this is just something for now to keep in mind as we move forward as a useful concept. And now let us consider as our initial data being a manifold with a metric G of signature. And let's furthermore consider that this choice of manifold with a metric is such that it's also possible to construct the corresponding pin bundle for this manifold with this metric, right? Which is just a principal bundle over the manifold with the corresponding group being the group pin PQ, and then the pinner fields, or like the mainstream way to see them would be to see them as the sections of the associated vector bundle, right? That you can see there, where the representation of the lowercase sigma would be the pinner representation of the pin group, and the big sigma is the corresponding vector space of the components. But again, in analogy with the tensor fields, here we are going to prefer to see these pinner fields as the corresponding equivalent functions on the pin bundle with the values in the vector space of components, right? Where then, of course, the derived action of the pin group in the fibers of the pin bundle corresponds to the change of components via the pinner representation of the pin group. So that's just an analogical case to the case of tensor fields. Right, and now, as I mentioned, our goal will be now to lift a vector field from our manifolds to the total space of this pin bundle, and then the action of this vector field on pinner fields seen as functions like this, then that is going to provide the corresponding Lie derivative for us. So let's see how this lift of the vector field may be constructed. So once again, our initial data is going to be the choice of the manifold with the metric and the pin bundle of the manifold. And now, sorry,
maybe I'm the only one not knowing this, but what is the field group?
It's like this. It's so you do know how the spin group is constructed out of the Clifford algebra.
Okay.
So I have to remind myself of how this is done. So if you take right, so to construct the spin group, you are taking elements with in the Clifford algebra which are normed to 1, and you have to take the point is that the spin group ends up being stuck. Would you have the full job? No.
The crucial term is length of the element there. So you don't take only even elements, but you take arbitrarily
Yes.
many multiples.
So in the point is that in the you have these elements that that are known to 1 in the like it's known to like E alpha, and the lowercase of I can use, right in the Clifford group, and now we will take elements of the form, right, the even number of these in the product. So these will form the right, this is of signature PQ. This would form the spin group, and you can leave out the rule that you have to have the even number, and that this would constitute the spin group. So so spin group is a subgroup of the pin group, but the cases, as I mentioned, they are analogical enough. So basically, you can imagine just me talking about spinors actually, and everything should work fine.
So pin group is just a double cover of the double cover. Yep.
Oh yes. So now we have the choice of pin bundle, and now we also know what it is. So it's cool. And to every definition of a pin bundle over a manifold, it comes with also this surjective map from the total space of the pin bundle to the total space of the bundle of orthonormal frames over the manifold for that particular metric G. Where this surjection actually is also compatible with the actions, the right actions on the two principal bundles, which is expressed in this diagram, where I should say that the map phi you can see there is just the double cover of the orthonormal group by the pin group, right? So basically, what this diagram essentially tells us is that fiber-wise, once you identify the fibers of the principal bundles with the groups, right, being the pin group and the orthonormal group, respectively, then fiber-wise, this surjection just becomes the double cover on the fibers, and therefore it leads to the fact that also you just extend this along the manifold, right, and therefore also as the total spaces of the principal bundles, right, the pi is just a double cover of the total space of the orthonormal frame bundle by the total space of the pin bundle. And so you can kind of sum up this situation by saying that we essentially kind of have this sort of tower of principal bundles here over our manifold with the two floors, right? So you have the orthonormal frame bundle on the first floor, and you have the pin bundle on the second floor, and we have the surjection pi in between them. And now, because of these sort of nice properties of the pi, you can actually construct unique lifts of right, the vector field flows and also the vector fields themselves. Therefore, from the total space of the bundle of orthonormal frames to the total space of the pin bundle, which is kind of a key trick in this process of constructing the Lie derivative, which is, by the way, also why I chose this very cool font to denote this step for my attempt to kind of attract your attention, because right, as I mentioned, our goal is here to lift the vector field from the manifold M to the total space of the pin bundle, right? But this possibility of constructing the unique lifts of vector fields from the frame bundle of orthonormal frames to the pin bundle is going to actually make our work easier, because now it's enough to construct the lift of the vector field from M to the bundle of orthonormal frames, and then we can uniquely lift it to the pin bundle to construct our actual Lie derivative. And so this is actually a kind of trick that we can use here, and it kind of helps us because, as I mentioned, the problem of dealing with the spinors at different points of the manifold for different metrics is kind of a more abstract problem to deal with, and this way we will be allowed to kind of only deal with the problems of different having the different orthonormal frames with respect to the different metrics at the different points. Right? So it's kind of more easily accessible problem, so to speak. So this is something that can be used, and maybe I should also mention that essentially by constructing the lift of the vector field from M to the bundle of orthonormal frames, now you can consider also your arbitrary tensor fields on the manifold as the equivalent functions on the total space of the orthonormal frame bundle, right? Once you have a metric on your manifold. And therefore, by doing this, we are actually also going to define in this process an alternative Lie derivative acting on the actual tensors on the manifold, which is actually different from the ordinary Lie derivative. So there is some kind of interesting geometry happening at that level, sort of also. But if from the perspective of this talk, we are viewing this step mostly as an auxiliary step to help us define the Lie derivative. But so I just wanted to mention that that's happening also. So let us now see how the vector field may be lifted from right from the manifold to the total space of this bundle of orthonormal frames. So I call the lifted vector field XO here, right? The one on the total space of the orthonormal frame bundle. And so to see what the value is of this XO at the point F, which is now an orthonormal frame with respect to the metric at some kind of a point of our manifold, right? So what you can do, once again, you construct a curve starting at F, and then you will differentiate it. And so let us now look at how this curve is actually constructed. So the first thing you do is you just do the same thing as when constructing the ordinary derivative. You compute the push forward of the frame. And this gives you, right, for every value of t, this gives you a family of frames over the shifted points. But our problem now is that there is no reason for these transformed frames to also be orthonormal frames with respect to the same metric at the different points, right? Because the vector field flow doesn't have any way of knowing about the values of the metric at the other points. So this is so far not a well-defined curve on the actual orthonormal frame bundle. But what you can say actually completely tautologically about these transformed frames is that they obviously are orthonormal frames, but not with respect to the original metric, but with respect to the metric which is given as the pullback of the original metric by the inverse vector field flow, right? And so this is where the connection plays the role in the connection on the principal bundle of the space of the metrics, right? Because now we can use the parallel transport for that connection to actually map these frames which are orthonormal with respect to the wrong metric to the frames which are actually orthonormal with respect to the original metric at that point. And this actually allows you to define properly the curve on the orthonormal frame bundle on its total space. And essentially that allows you to define a vector field. So I believe this is a very cool trick that can be kind of used to actually properly lift the vector field onto the total space of the orthonormal frame bundle. And maybe we can look at the same situation also fiber-wise. Right, so what happens after you compute the first step, the push forward of your frame, then your result kind of ends up here, right? So it's in an orthonormal frame bundle, but the wrong orthonormal frame bundle, so to speak, right, with respect to the pullback metric. And so we would like to actually have the result in this frame bundle on the right. So we would like to have it in the fiber over the same point of the manifold, but in a different orthonormal frame bundle, right? So in my mind, this kind of describes where the problem is with right, defining this Lie derivative for these objects which also depend on the metric. But now, sort of looking at the same situation from the perspective of the principal bundle of the space of metrics, then these two fibers are also, by definition, just two different fibers in the same principal bundle, just being fibers over the two different points, right, being the two different metrics. And so then in this language, you can actually use the connection there and parallel transport for it to actually kind of connect these fibers and actually properly define your curve on the total space of the orthonormal frame model. Right, and so as you can see, then to construct the vector field, you are actually differentiating it with respect to t, and therefore it is truly enough for you to have the parallel transport for the infinitesimally closed matrix. So everything works fine.
Just can I ask a big question? So of course, if you have a metric, then you can also just use the Levi-Civita connection as a connection of the orthonormal frame model and simply do the horizontal lift that vector field from downstairs. You take vector field, you lift it to the vector field on the frame model, like you do the horizontal lift by Levi-Civita connection. How different is your lift from the?
So there actually is a relationship yes, there actually is a relationship. It can be actually expressed once you switch back to the language of associated vector bundles. There is actually, you can formulate a relation between the covariant derivative of your spinor fields and this free derivative, and there is a difference between them. Yes, but I don't remember the formula. I'm sorry.
Yeah, so like lifting Levi-Civita, the thing you get is what people call spin connection. That's a connection, so it's tensorial.
Yeah.
This is a different object, so it's not tensorial.
Thank you.
But they are related, and the relation is important.
Yes. So thank you. That was a good question. So yes. So this is how you now lift the vector field from. So now you have your vector field XO on the total space of the orthonormal frame bundle, and all this is left to do is now uniquely you can lift it against the direction of the surjection pi, right? To actually obtain the XP vector field on the total space of the pin bundle, and that is essentially what we are trying to construct, right? So now if you have your pinner field as the corresponding equivalent function on our pin bundle, you can now act on it with this vector field XP, and that is going to give you the equivalent function that is the result of your derivative, the resulting pinner field, right? So yeah, this is how things can be figured out in the classical case. So maybe before I move on to the generalized case, I could ask if anyone has any more questions.
Is there some good one sentence answer why I would be interested in those derivatives? Like, is there some immediate
in the generalized, I think?
No, in the classical setting.
I'm not sure about the classical setting. Fritz was describing me why we are doing this in the generalized setting, but he knows a lot more about it.
Well, it's in the real world you have different invariants and you have fermions, just filters. So you want to understand how one acts on the other.
Okay.
Like if you have standard model and you add gravity to it, then you need.
Did it answer the question? Or?
Yeah. Okay. So, for example, we would like to have fermionic fields, spinor fields, which are invariant with respect to some vector field.
Yes, or you just want to know how different films act on filters.
Okay. And you don't want to use the spinor connection to do that?
No, because it's not how different films act. They act by the leader.
Okay. Thanks. So, anyone else would like to ask something about the classical way of doing things?
I would like.
If you push forward the frame, you said there is no obvious reason why the new frame should be orthogonal.
Yeah.
But you can always do Gram-Schmidt, right?
Okay.
To make it orthogonal. Would that kind of help or not?
I haven't thought about that.
This is the construction of the Levi-Civita connection, actually.
But for indefinite connection,
Okay, sorry. Yeah.
Simpson.
Was there another?
Yeah, hi, Fred. I wanted to ask just notation. In the previous slide, you had this BG, and this BG was that identification of orthonormal frames. Yeah, in Formula 9.
That denotes the parallel transport. If you are the B with the two different metrics, you mean?
Yeah, so that was what was I said in like Formula
That
7.
denotes the parallel transport for the connection on the principal bundle over the space of matrix, and
Okay.
it's the parallel transport between the two fibers over the pullback metric and over the origin metric. Right?
Okay, thank you.
Yeah, so this is like a point-wise, so to speak, version of right. Point-wise, we have the connection over the tangent space at that particular point.
Yeah, thank you.
Which we are dealing with, so to speak.
No, sorry, I'm sure this BG shall be somewhat invariant with respect to some group, or if it's something like a principal connection. And it should not lose the fundamental vector fields and and the variable definition. But what do you suppose about the BG?
I'm not sure. I'm just sure that this map, once you compose these two, it actually gives you an equivalent map with respect to the action of right.
Okay, which gives the isomorphism. And isomorphism.
Yes.
Vector or
Yes.
Okay. Which is basically the same as a collection.
All right, so I guess we can move on to the generalized case. And so in the case of generalized geometry, I'm going to first tell you about the spinors on Courant algebroids in generalized setting. And we are going to talk about Courant algebraic automorphisms, and then we are going to actually see how this similar result may be formulated on Courant algebroids. So I have also included the definition of the Courant algebroid here, but I suppose in this audience, I guess everyone has at least to some extent encountered the definition. So maybe just to remind you of the notation, right? So a Courant algebroid is a vector bundle E with some extra structure being the anchor. We're going for a morphism from E to the tangent bundle over the base manifold M. Then you have the pairing on the sections and the bracket on the sections. And so these are moreover these satisfy these further axioms which make them kind of compatible with each other, right? And so this is where our spinors are going to lead in this case. Now there is a natural way to also define a Lie derivative in this generalized setting on Courant algebroids. So you can compute the Lie derivative in direction of any section U of the Courant algebroid. The way it acts on functions is given is provided by the anchor. The way it acts on sections is given by the bracket of sections. And so that's kind of the most important reason I just decided to include also this series, just for us to realize that in this generalized setting we are going to be looking to compute the Lie derivative in direction of sections of the Courant algebroid rather than. So the kind of first obvious thing we need to realize is we are going to need to replace the vectoring flows generated by vector fields by some kind of transformations of the Courant algebroids generated by sections. Then we can look at the definition of a generalized metric on a Courant algebroid. It is defined as subbundle V plus of the Courant algebroid such that the restriction of the pairing on this V plus gives you a non-degenerate metric on V plus. Now, I guess many times if you look up the definition of the generalized metric, there is some further requirements, and this is kind of the minimal version because you want it to be as general here as it gets. So this is the only requirement for the subbundle V plus. And we moreover just assume that the restriction of the pairing onto this V plus gives you a metric on V plus of signature PQ, which is not really a requirement, right? Just tautologically there is going to be some kind of PQ there. And the only thing we really require is for V plus a vector bundle with this metric given as the restriction of the pairing for this to admit the pin structure, right? So that again the pin bundle over our manifold for this metric vector bundle given as V plus can be constructed, because we will be interested in spinor fields on this V plus for this metric structure, because these turn out to play an important role in generalized geometry. So now let me tell you about Courant algebroid automorphisms. So as I mentioned, we are going to be looking to find some transformations of Courant algebroids which are generated by its sections, and this role turns out to be played by these Courant algebroid automorphisms. So let me tell you what these are. So a Courant algebroid automorphism is an automorphism phi of the vector bundle V, covering phi bar, being a diffeomorphism of the underlying manifold, such that it has these natural action on sections, and moreover, we require naturally for it to also be compatible with the structure on Courant algebroid, right? So compatibility with the pairing with the anchor and with the Courant algebroid bracket. And what is particularly interesting to us is that each section uniquely generates a Courant algebroid automorphism like this. So I should say each section generates a whole family, in fact, of Courant algebroid automorphisms, because you can uniquely assign to each section U of the Courant algebroid a vector field ZU on the total space of the Courant algebroid, such that it covers the anchor of the section, being the vector field on the underlying manifold, right? And so once you look at the vector field flow of this ZU, then for each value of the parameter, this is going to give you the Courant algebroid automorphism like this. And so this vector field for a corresponding section U can be actually constructed based on these two requirements. First of all, it has to cover right the anchor of the section, being the vector field on the manifold. And once you look at the flow of the vector field and you examine its action on section, right? Actually, we are looking at the infinitesimal version of the action on sections, and that simply has to give you the bracket of the section U with the section V you are acting on, right? And so this allows you to construct the vector field ZU for the corresponding section U. And just to remind you, what is going to be important for us, that these vector field flows generated by this vector field are these Courant algebroid automorphisms, which means in particular they are of course compatible with all the structure, but in particular they also act as isometries with respect to the pairing on the Courant algebroid when they are mapping these vectors in fibers of the Courant algebroid. So this is going to be particularly interesting for us. And now the rest of the procedure is very analogical to the classical case. So first of all, let me mention the connection on the principal bundle over the space of generalized metric this time. So here the underlying manifold is the space of generalized metrics, right? So these are the different choices of the subbundle V plus, such that the restriction of pairing gives you the metric of signature PQ for these. And the fiber over each of these metrics corresponds to the orthonormal frames of this V plus with respect to that restriction, right? So you obtain a principal bundle with for the orthonormal group, in this case again. And now, if you are looking to construct the infinitesimal parallel transport for your connection, so now if you want to connect two fibers over two different infinitesimally flowed metrics, that is also important here. Being fibers over this V prime plus and V plus. So here you should think about this as being like just infinitesimally shifted to two different infinitesimally shifted choices of the subbundle V plus, right? And so if you want to map an orthonormal frame with respect to the prime V plus to an orthonormal frame of the actual V plus, in this case, it turns out that all you need to do is simply to compute a projection of the vector onto the new V plus, right? And this in the first order, right, infinitesimally, this turns out to actually give you the canonical isometry. So this is actually even simpler in this generalized setting than it was in the classical case. And now it is also naturally possible for you to construct a bundle of orthonormal frames for your choice of V plus right, being a principal bundle of the orthonormal group over the manifold. And by assumption, we also can construct the pin bundle for that V plus. And again, there is a double cover surjective map on the total spaces, going from the total space of the pin bundle to the bundle of orthonormal frames over V plus. And now, again, these spinor fields in generalized setting can be seen as equivalent functions on the total space of the pin bundle. So you would like to have the lead derivative as a vector field which acts on these, so such that it gives you, again, an equivalent function as a result. And this way you can extract the lead derivative. So we will be again looking to construct a vector field on the total space of the pin bundle. And again, it can be done in such a way that you lift a vector field from the total space of the bundle of orthonormal frames to the pin bundle, and that is going to be a result. And right, the only difference is that this time we are assigning this vector field to a section of the Courant algebroid rather than write the underlying vector field on the manifold. And UP is what I call the vector field on the pin bundle associated to a section P, so section U, sorry. And so, right, again, the first step is to construct a vector field for the section U, which is a vector field on the orthonormal frame bundle. This one I call UO. And so its value at the point F, which is an orthonormal frame for V plus, can be constructed. Again, this is very analogical to the classical case. We construct a curve and then differentiate it. And so this time you first act on the frame with this family of Courant algebroid automorphisms generated by your section U. Now again, you run into the problem that there is no reason for these transformed frames to be again orthonormal frames at the different points with respect to the same V plus. But here it's completely tautological actually, right? It's obvious that these transformed frames are going to be orthonormal with respect to a different choice of V plus, which is such that you transform the original V plus by the same transformation which you use to transform your frame, right? So this is actually kind of very tautological in this case. And so you can just post-compose it with the parallel transport for your connection, which, as I have mentioned in this case, is just projection into V plus. So in this case, you can, in this sort of very, in a much simpler way, I would say, you can construct this curve on the total space of the orthonormal frame bundle, which then you can just differentiate it to obtain a vector field on the on this total space of the frame bundle for V plus. And now you can uniquely lift it against the surjective map from the pin bundle to your orthonormal frame bundle to obtain the vector field UP, which you are looking to construct. And then once again, if you see your pin field as the equivalent function on the pin bundle, then you can just act with this vector field UP on it, and that provides you with the result of your lead derivative. So, this is how things may be translated onto Courant algebroids. And yes, finally, I have just given you a few references of the most important works we are looking at while working on this topic. And I would like to thank you for your attention.
Thank you very much. Questions?
How do you get the map B from BV plus currently to this calligraphical and
In the classical case, you are asking what?
probably yes.
Oh, it's in the general asking. I think about it. All right, so you have to think. So you are now in just one fiber over one point, right? So you have your fiber being the vector space of the Courant algebroid, and you have a different choices of V plus being right, being just the different subspaces of the fiber, and
I can fix a positive definite matrix, so I can fix P0 to have some bundle of
right. So I believe this.
I check project. into something which is a compound. It's the polynomial compound.
Right, so I will discuss completely tautologies, right? So if you have a choice of frame which is such that it determines essentially the choice of B plus. If you have a frame, this way you determine the choice of B plus.
Metric.
I'm not sure if I understand the question correctly.
So, okay, so, basis, determines, metric in a vector space.
Yes, yes,
Order basis.
yes.
And, you speak about, if I got it, kernel MB plus is a generalized matrix, or all metrics, let us say the classical case, matrix. So, in a way, it is subjective for this. I don't know, I was thinking about it once.
I believe this
I
is
don't know.
very analogical to that. So it's just a different viewpoint on the same thing in my opinion, because right in the classical case you have the vector space with different metrics on it, and here you have like a fixed pairing on the whole bigger vector space, right? The fiber over Courant algebroid, and you are instead choosing different subbundles onto which you restrict the same pairing, but it's just a different way to describe a singular.
So maybe I have a GLN. Sorry. So I start with a GLN R bundle. In the classical case, I start with a GLN R bundle, and then to any frame which looks like any frame, I just assign a metric for which this frame is orthonormal and
Mhm.
maybe ordered. Yeah. So I start with a GLN R bundle. This would make sense that GLN is no. It's any frame can be viewed as orthonormal if you say to the matrix B such that the frame is.
So yes, I think I see what you mean, but
So the difference here is that there is this is all living ambient space, which is a metric. So
This is maybe
so the fact that a priori from the beginning there are orthonormal frames. So I guess
no, other topologically, sorry, I don't understand it topologically. So then the map is not surjection because if P is positive, Q is 0. I have OP bundle, which is a bundle of compacting groups, and suppose the manifold is compact. So I have a compact total space which cannot surject on something non-compact because space of matrix is a cone. Because any metric can be multiplied by R plus. And then it's incompact.
so in my mind, it's just for instance, when it was
So I don't understand it. But then it's more.
so once you choose the signature PQ, right, then you would be just using
Positive definite.
yes. So such combinations of P plus Q number of elements are independent, such that the pairing on them gives you right the
So you could have the choice Q bundle over a compact manifold, but inside E, which is not compact.
So I felt like that's why I didn't even write out the projection because I felt like it's kind of tautological. Now that I think about it, maybe I should have, but it's just right. You have the frames which define the same B plus are exactly. You have to consider only frames which are orthonormal with respect to the fiberwise pairing, right? And out of them you choose such that the signature becomes PQ, and the choice of frame is the choice of B plus. So it's the projection is just
Now, actually, so suppose, right, suppose we have a matrix B and take PG in the MB plus space. And in the MB plus space, in the space of MB plus, take a metric.
okay.
Generalized metric and multiply 2G by 2, by number 2. And I guess that space of generalized metric. And you must find two frames which cannot be simultaneously OPQ because one should be twice smaller.
That's apply generalized metrics here. I mean, generalized metric here is just a subspace. It's the data of the subspace.
Yeah, I don't understand the construction technically, but I believe that might have some, then it might have very sense.
Not this helps, but like you can say that this MV plus, this is, so it's a vector space with some, this is point point, right? So this
Yes.
a vector space with some p, with some pairing of some signature, whatever. Then it's MV plus, the basis of that thing, that MV plus is the space of all subspaces on which the matrix has some, the induced matrix has some signature. So it's like collection of matrices. And then this fibration, this BV goes to MV, like the fibers of that are given by choices of frames on that subspace. So both BV and MV are non-compact.
Yeah. It's a OPQ bundle over what? So it's a OPQ bundle on M or on E? First question.
MV plus.
Over MV.
MV plus.
Yes.
Yeah, but okay, but it's OPQ bundle over MV plus.
Yeah.
So the signatures, okay.
Good. Any further questions? Also from the online audience?
I have maybe a very like basic question, but so I don't understand completely why there is this property that if you have a nearby metric, you can identify orthonormal basis for this matrix. But do you know for which other geometric structures, other than metrics, a similar property would hold? So you could replicate this story, but not for metrics, but for something else.
I'm only aware about metrics. I only learned about even that this can be done for metrics, like as I was working on this. But it's an interesting question, but I'm not sure honestly.
And do you have maybe like a geometric intuition for why this works for metrics? This identification?
It's a good question. Right, so honestly speaking, no would be the answer, but yeah, I don't think so.
Okay, thanks. Okay, yeah, thanks.
It's certainly interesting, and also that can be only done in the infinitesimal case, like this sort of canonical. So it's
That is not very surprising. It's like if you imagine that there are like you have like this nice frame and then you have other frame and it starts rotating, then if it rotates a little, then you can kind of identify things uniquely. But if it rotates too much, then it becomes, then it becomes difficult to identify things. This is like, it's similar to deforming subspaces and so on, I think.
okay.
Yeah. Okay, thanks.
Yeah, thank you.
Yeah, any further questions? But if not, then let's thank our speaker again.